So last time what we did, we talked about lots of applications. I was inspired by the idea explaining you that biology, nature in general is amazing, and the idea of application or optimization is done by the natural selection, and the best shape wins at the particular situation. So if the forest is very windy, like if the place is very windy, like palm trees, they have their own different leaves so the wind can go through and don't break the palm tree. Apple trees usually don't have to be afraid of the wind, so they have this kind of shape to maximize the area for the sun, and so on. So nature does that. What is the optimal shape for the ladybug to fly? Hemisphere. So it's pretty cool. And then I was telling you the eyeball has a shape of the sphere, and we just got this perfect shapes of the square, circle, spheres, and so it's pretty cool that nature actually does those. Anyone else have good examples? Did you think about it? Because Chris was criticizing me after the class. No, nature sucks and so on.
Well,
but I think
my point was that nature doesn't pick the most efficient route.
I think it just doesn't like biology class. So
that wasn't my point.
Anyway, we did the example last time. I'm joking.
Also, by the way, another example was animal cells in general.
And then we did the example about the fence. There was the idea, what is the best fence to build if you have fixed amount of the material, not to waste too much, and not to have like extra space left. And the best shape was a square. So if there are no restrictions, the best shapes are squares and spheres, circles, and cubes. That makes sense. But if there are restrictions, then these shapes will be changed. So let's see. In this case, there are restrictions, and this is a minimization problem. Last time we were maximizing the area to build. This time we want to minimize the cost of whatever we plan to spend. We like to put this example on the exam, by the way, in the first one. This is a minimization problem. How do I know? I read. It says minimize the cost. So this is minimization problem. Minimization problem. Very typical. In business, we teach maximizing profit, minimizing cost functions. So remember steps. Step 1, sketch the graph, which is this word, and then mistake, T-C-H. Okay, next, sketch the graph. Sketch not the graph, sketch the picture. At least try to imagine what the heck is going on. It says rectangle garden. So you see, like, I have to read it in English, right? And that's not my first language. As an international student, I don't like that. I want to see math. And I think many of you have the same mindset, like, math, where is my equation? Give me equation, I know how to differentiate. I know how to find critical points. But no, we try to teach you to create a model by yourself. So that is an experience of modeling firsthand. And I taught myself to read it fast as an international student to speed up on the exams. So I like, enclose, that's a weird word, by the way, but they say rectangle. Okay, I know how rectangle looks like, so I will draw a rectangle. Width area, 1,000. I'm like, okay, I can read that, right? So that's a good example as English of a second language, or how to speed up your reading. Make a sketch and write down the information. Let's call it A, area is 1,000 feet squared, right? Square feet. One side costs $30 per feet. Oh, so we don't have the size of each side. We have the price of each side. And it says one side only is 30 cents per feet. Dollars, yeah, dollars per feet. So cents will be too cheap. So guess, any guess is fine. Mathematics will fix you later. Let's say this one. Maybe this one costs $30 per feet, yeah. For example, there are rocks there. So the fence is built and 3 sides are cheaper because you can just put wood, but there's a rocks underneath that side, so you have to make it more stable, and that's why it's more expensive. And sometimes they do write all this stuff. I don't like too much writing, so I just shorten it, the problem. The other 3 are $10 each. So I know it's 10 here and 10 here. So again, it's not size. It's not 10 foot, kilometers, or whatever. It's $10. This is how it looks like. And then the area is 1,000. Okay, that's a nice sketch. What's the question? Find the dimensions of the area that minimizes the cost. I see. So I went to the store and I found the prices. For the wooden part in blue, it will be $10 per foot. And then for the metal one, it's more expensive, 3 times more expensive. And I don't want to waste too much money. Area is already fixed. I already have the backyard. So my area is fixed. It's my backyard. It's 1,000 feet square. So what will be the perfect dimension for that area that will minimize the cost? How much should I invest? We don't know the sizes of these. This is just approximation. How much should I invest into the expensive size? Maybe I should make it small and this long instead. Maybe that is the perfect size. So we don't know what kind of lengths each side should have, not to spend too much money, to minimize the cost. So let's again do the same thing we did last time. Let's call one side L and the other one is W. L is length. You have to write this down because you can also choose X and Y, D and M, whatever. So readers should know when they read your work, not squared. What is L? And W, width. X and Y is also fine. As you can see, length times width gives you A, feet times feet gives you feet squared. That's why it makes sense. A is 1,000. We know that. That was step 1. Step 2, make connections between whatever you just wrote. So you made up some names for the lengths and widths, X, Y, whatever you want to call it. A also made up name, area. I could call it J because I'm Julia. Step 2 is make connection between variables you just made up. What is the connection we can make between L, W, and A? Anyone else? Sorry, you just always answer. Yes.
L times W equals 1,000 or A.
Okay, perfect. L times W, yeah, I heard it. L times W equals 1,000. Do you all agree? It's area, so that is a connection between variables I just made up. A product gives me that A, 1,000, thank you, nice. And then, this is not what we want to minimize or optimize. In last problem, this was actually what we were maximizing. Not here. This is not what we need. We need to minimize the cost function, and we don't have it. So we need to build the cost function. Let's build the cost function, and sometimes in business we call it C. So cost function C. Let's see what C will looks like. So L is L feet long, $10 per foot. What is going to be the price of this side? This 10L, right? Make sense? Yeah. 10L. You're working 10 hours. You're working L hours, $10 per hour. It's 10L money, right? Now, who's playing with computer? How about this side? W and W width, $10 per foot. How much it will be?
$20.
$20 total. So 10W plus 10W. That is my width plus width price. And then one more left. How about the expensive side? How would I call that one?
30L.
30L. 30L is the expensive side. Does it make sense? So that's my width, and then length was divided into two situations, expensive and cheap. 40L plus 20W. Now we have two equations. L times W is 1,000, and then C, which is 40L plus 20W, is the second equation. I told you building a model means you're making a sketch of the picture so you can explain at the conference, oh, this is what we're doing. We are optimizing the fence. And then you have two equations. One is usually whatever we need to minimize or maximize. And the other one is constraints on the variables, restrictions. So what is my model here? What is the equation we need to minimize or maximize? C. Do you all agree? We're minimizing the cost function. The less this function is, the less money we spend. Because the units for this cost function are dollars. This is in dollars. While, so this is supposed to be a system, the L and W cannot be infinite. L cannot be like 1,000,000 and W cannot be minus 17. So these restrictions, not only coming from the domain that L and W better be positive, but also from the fact that you have finite number of square feet in front of you, 1,000. So these are called constraints or restrictions. We can minimize the cost, but only take into account that we have restrictions, that L times W is 1,000. And that is what you call a model. So this is your experience of building a model. I told you some universities have a class called modeling, and they do physics, biology, and math at the same time. It's very interesting. And you even have tools in your hands, and you play with them, and you try to build it yourself. We know how to minimize or maximize things. So remember, you have homework due tonight and stuff like that. You need to differentiate C. So I want to find C prime. But I cannot do it because it has two variables, and we only teach in calculus 3 how to do that using partial derivatives. So what I told you, step 3, was use the equation for constraints, L times W, which is 1,000, and solve for one of the variables. Solve. Why? When we solve one of the variables, we're going to plug it into C. And then C will have only one variable. Let's solve it for W. Doesn't matter if it's easier one way than another, then choose the easy way. In this case, I don't feel like there's a difference. So let's solve. We have W is 1,000 over L. This is not E, it's L. L. Now you can see that, you see, L should not be 0, definitely. And there's some kind of restrictions that L cannot be 1,000,000, then width will be infinitely small. So there are restrictions on the domain as well, but you don't have to know them, to be honest, all the time. Now, plug into C, into the function you need to minimize, into C. C will be 40L plus 20, and now instead of the W, you will have 1,000 over L. Now you have a function of one variable. Cost function now only depends on the length of the fans, because we found connection between L and W. So this is 20,000, right? If you simplify, C is 40L plus 20,000 over L. And we want to differentiate this. So you could create common denominator, which will make a quotient rule. I would not recommend doing that, but let's put it in the box to remember that this is what we're going to differentiate. I would differentiate this right away, which is step 4. Calculus starts now. Calculus. This is where we actually use calculus tools to find minimum and maximum derivative, critical values, minimum positive, negative, and so on. So, find the derivative. What is derivative of 40L? 40. And now, how would you find derivative of that other stuff? What? Oh, thank you. C prime. 40 plus. This, you can see it as a 20,000 L to the minus 1 if you want. Maybe this will be easier. So the derivative will be minus, what else? Thank you, you see? So if you do it quite a lot, you just see the pattern. Every time you have 1 over L, it will be minus 1 over L squared derivative. Or you can do the long way if you want. So we are minimizing this function C. And we know how to do that. You take a derivative, set it equal to 0, solve, blah, blah, blah. What are your expectations for the sign of the C prime if we plan to have a minimum here? Up, down, down, up, 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 down, down. Do you know what I'm talking about? The first derivative tells you when we increase or decrease.
Down, up.
Down, up. So I expect the first derivative to be negative. Then the original function goes down, hike down. Then it will be positive. Then this will indicate minimum. So we expect to have this even before we start. That's pretty cool. This is my first derivative. I need to find zeros and D and E points. Here, I highly recommend to create a common denominator. Then you will not make mistakes. You see a fraction and a piece, or a fraction and a fraction, create a common denominator. It will give you 40L squared minus 20 thousandths. And now, you want to find zeros in D and E points, which are called stationary and singular points. Numerator equals to 0, 40L squared minus 20 thousandths equals to 0, gives you the good points, the stationary points. But denominator equals to 0 also should be counted. That one gives you singular points. Maybe there's a cusp, and 0 might be in the cusp. Does that make sense? So this one is easy to solve. 0, L is 0. Let's keep it and check. And then the second one, the first one actually, we have to solve. Does that make sense what I just did? The top 0 and the bottom 0 gives you 0 and D and E points. Fraction. The denominator should not be 0, so you solve these points. Isolate the unknown. That's how I usually explain. So 40L squared, I'll keep it on one side. Divide by 40. L squared will be 20 over 40, well, 20 thousandths over 40 is 500, yeah? 500. 5 times 4 is 20. Then L will be a square root of 500, yes or no? Both are correct. So you're correct saying plus and minus, and you're correct that no, only plus, because L cannot be negative.
Actually, I wasn't correct with that. I was saying you said a square root of 500. And there are 2 of them, so.
Okay, you don't catch my English, so obviously I don't.
Sorry, I actually wasn't certain with what the.
That's funny.
Of questioning one.
That's funny. I said a square root, and he's like, well, it should be 1 then. No, I don't know what I'm saying.
Well,
you do understand this, right?
And either one is fine.
No, that's not how it is. It's funny.
I wasn't sure what you meant by that.
So, both are correct. We need to exclude the negative sign. So how to I will circle the positive instead. I will even circle the positive like so. Domain, right? So I'm excluding negative. What else should I kick out?
Sorry.
L is 0 is also not in a domain. Not in the domain. If you repeat, if you check what's the definition of critical value, it's supposed to be in a domain. So only 1 point, L equals a square root of 500. This is a critical value. So a student who was following me after the exam, the first exam we took, was very upset because he failed it. And then I told him, if you want to keep following me, actually in a hurry, but let's go. And he said, yes, it was too long. I could not finish on time. And I said, let's go with me. I plan to cut corners on the exam. And he got so happy. He's like, you're going to cut corners? I'm like, yes. I don't understand why it makes you feel so happy, though. And then he's like, oh, you mean literally? I'm like, I always mean literally. I don't use phrases, okay? So I take scissors and I cut all the corners of our exam to scan them. Right? But he thought I meant I will drop some problems. Because it's kind of close to that, cutting corners. So now I know the phrase, cutting corners.
That's actually an awkward interpretation. Because
yeah, that's interesting.
Imply would be making it easier for you.
No, for everyone, for everyone.
Because cut corners kind of implies that you're doing bad work to make it easier.
Oh, I see. Yeah, I don't know. He just felt happy for a second, and then you can see his face expression was like, down. So, critical value, what do we do now? Number 4. So this was step 4 calculus, but we do know what we do now. We put everything on a sign line. So it's my L, which is square root of 500. Sign line for what function? Who knows? C prime, thank you, derivative. And also, to be honest, it's not from minus infinity to infinity, so kind of we should put that it is from 0 to something on the right. I don't know what it is. Some kind of domain will be on the right, but at least it's not negative. Okay, I don't have a feeling what a square root of 500 is. For applicational problems, it's nice to do approximation to know which test points to choose. What do your feeling is?
It's higher than 20, but lower than 30.
Very nice. Yeah, this is very good. You all should have approximation in your mind At least it's not magic. You need to train it. It's like with the temperature. You know that 78 is nice, but like 95 Fahrenheit is hot. So the same thing. There's some kind of feeling about it. It is true. 2.2 and 36. Good job. Very good. So test points. We even know what we expect. Up, down, and up, because we want to have minimum. We're minimizing c. We're minimizing the original function c. We take test points on a derivative. What kind of test point do you want to take? Cannot take 0. Do you know why? 2 reasons. It's not in a domain, and where do you plan to plug them? You plan to plug them into this box. You cannot plug 0 there. And that's why I decided to exclude it. So, well, you could try, and then you will notice that you divide by 0. What is the next easy point to the 0?
1 is good.
Yeah, 1 is good. Did someone mention 1? I heard. 1 is a good point. Take this one, plug it into one of these 2 boxes, whatever you like. I just care about the sign, positive or negative. I would like this one. Positive or negative? Negative, right? Because 40 minus 20,000 over 1 definitely is negative. So I will put that the first derivative is negative, but then the original function is decreasing. That's what we expect. What other test points bigger than 22.36 you want to take? What do you like to take?
100 quite convenient.
100. Might be outside of the domain, we never checked, but let's try. 100, positive or negative? Well, 40 is positive, minus, kind of interesting. L 100 will have 4 zeros, right? So what do you think? Positive or negative?
No, we get 40 minus 2.
Yes, exactly. Do you agree that it is positive, or should I show you? So let me just show it to you really fast. If I plug 100 into the function c prime of 100, it's a test point. Just test. It will be 40 minus 20, 1, 2, 3 over, but 100 squared will be 1, 2, 1, 2 zeros. How many zeros goes away? 4 zeros. 40 minus 2 is positive. Check. Or you can use your calculator. And that's what we expected. Minimum. We're excited to get minimum because we are minimizing the function. It's applied to application, so we don't expect many troubles here. Ask me, what do you think? Agree? How's your calculations? Yeah.
That's interesting.
Now,
I just never
since there, let me zoom in. What is this since? There are no other critical values and the function is continuous, then this local minimum. So remember, this is the first derivative test. It shows you local minimum, not global minimum. Global minimum, you have to check the endpoints and stuff. Local minimum is also a global minimum. Global minimum. Because in order to have a more minimum that we already have, the function should change the direction. To change the direction, you have to have one more critical point at least. And we don't have any, so that's nice. Now, global minimum, we wanted that. So now we can conclude answer. Answer. The answer is length was found as 1 square root of 500. Width can be found from the relationship, which we know 1,000 over L, 500, the square root of 500. So the first answer is approximately 22.36 feet. The second answer, this is the exact answer, but approximately it's 44.73 feet. That's nice to answer for engineers, so they have some kind of approximation. And then the cost function. The cost function had a formula, 40L plus 20W. Or you can use a formula with one variable if you want to, but it looks harder. Plug in, you'll have 40L is a square root of 500 plus 20. W is 1,000, the square root of 500. That's the exact answer, which is approximately let me move it down, approximately $1,788.85. That is a minimum cost with the given dimensions of the fans. To minimize the cost, this is minimal cost. How do you feel about this? So dimensions and then a cost function. Is it hard? Like, I can review if you want the whole problem. We had restriction with the feet squared, which was area. We build the area. Area is L times W. But then we had cost. If you remember, the cost was different on 4 sides. We did not know which ones. They said 3 sides are cheap, 1 side is expensive. We made a guess that this one is expensive. How much was it? 30, I think, $30. This one was 10, 10, 10. So by building this model, we minimized the cost function, and this gave us critical value. Critical value took us to the first derivative test. It gave us down and up minimum, and we justified that this is the global minimum L lengths. Plug it in, got the answer. Do you see that my math actually fixed something? So width, that's an interesting thing. I always like to point this out. Width is longer than length. Do you see that? That's why I put the approximation there. Width, which is supposed to be short by the name of width, is 44, while length is 22. That makes sense. It was actually dumb from my side, but I always do it on purpose, to choose the expensive side to be the longest one. Would you do that? Like, you know that it doesn't matter where to put the expensive side, but somehow you choose the longest one to spend money on that? That's just dumb. So I chose it on purpose. Math showed me the minimum and switched the sides. So actually, for the engineers, you will produce this result, and the engineer will be like, did you just say your length is twice shorter than width? And you're like, yeah, just rename them. You can call them X and Y and rename them. So actually it says that width will be 44.73, which is length, right? It's longer, 44.73. And then this side will be 22 and 36, and 22 and 22 and 36. And then the shorter side will be more expensive than the longest. That will save you money. That makes sense. That's kind of the idea here. So I would say new length is actually 44.73, and then new width is actually 22.36. That is why we use X and Y as mathematicians, because we don't want to get confused. That's why we like it so much. We like X, Y, Z, T for time, D for distance, and for normal usually and stuff like that. Because then you can name it whatever you want. The longest side called length, the shorter side called width. So that's a pretty cool idea that math fixed it by itself. Make sense? One more problem. So I'm switching. Are you done? Usually you're looking at this too. Good job. One more problem is continuation of the chapter, but I do like to call it open box problem. It's a very known problem. So please write it down. A box is made out of 10 centimeters by 16 centimeters piece of cardboard. Squares of side length X centimeter will be cut out of each corner, and then the ends and the sides will be folded to create a box with no lid. So it's open top. Find the dimensions of the box. There should be S over there to maximize the volume and find the maximum volume. So here's the picture. We have a cardboard. Well, I will wait for you to write down. And I have nice animations also. You have a cardboard. This is so you want to create a box because you work at FedEx and they're out of boxes. Well, that's kind of a weird idea, but why not? And no lid. How will you do it? You will grab scissors and you'll grab a cardboard. Apparently, you found some random cardboard which is 10 by 16 originally. And then you kind of have intuition that if you cut off the corners, it will fold nicely into this box. The box will be smaller in shape than the original cardboard, but at least it will fold. and it will be no lid, but you can put some like candies inside and stuff. So very interesting idea. I like to show this picture of FedEx because have you ever asked yourself why the FedEx and other companies have such a typical shapes? Again, the optimal shape. If your only job is to maximize the volume, it will be a cube. And that is why these boxes are the most popular. And these one, small cubes and big cubes are the most popular boxes because they maximizing the volume inside. And you want to put as much stuff you accumulated in your garage as you need, right? When you move. So that is the idea. These weird looking boxes created for the specific objects like tall chandelier or wide something. But in general, cubes are the best shapes to hold things. And these are for letters, for example, in books. So again, optimal shape is a cube after all. We are not going to have a cube in this case. Why? Because there's no lid. The lid will be saved so we can make it taller now or wider. So when something is missing or there's some restriction is in front of you, that makes a different shape. If there's no lid, there's no roof, right? You can make it different. Here is the idea. And I have several cool animations to show you. When I was teaching it the first time, there were no animations. Now it's very nice. So you have, I usually bring the paper and I cut it in front of people. You cut the corners and you fold it into the box. Look at that. The thing is, you don't know how much to cut. Obviously, the cut better be the same, or else you just really bad at cutting, right? But if you cut the same, it should fold in some kind of box. What kind of cut we should do to make a very good box? Should we cut a little bit? Then it will be very flat. Should you cut too much? Then you're wasting material. So that is a nice idea. And then here it is. And here's a very nice way to show you this. I include this link so you can also play it later by yourself. This is some kind of different restriction, so it's not particularly our problem. But look at this. So the cut is, let me see. Let me increase. Okay, good. And H. So the cut is, here's the flat piece of cardboard you have. My cut is different. Maybe I decide to cut a little bit. Okay, so I chose the cut. Now I'm cutting it off, and now I cannot redo it anymore. So you cut it off, that's it. I'm folding the box, and it looks super small. What can you even put here? A painting? So you want to optimize or maximize the volume. Okay, so like let me cut more. The more you cut, the more it folds. I cut a lot. Folding. It's good. If I cut even more, it becomes too tall. So there is some kind of optimal way to cut. And I will show you how again. Flat, fold. Flat, fold. Is it pretty cool? I just like to play with it, so it's kind of the idea. But the thing is, we will create this function. There's a function on the left-hand side. This function has a maximum. Look, when I'm changing my cut, if I cut 0, it will stay flat, duh. If I cut too much, I'm wasting lots of material. There is an optimal cut, which is over here at the top. You see how the point is moving left and right? At the very top over here is an optimal cut, which makes it very nice, almost cubic shape. And that's what we're doing here. Let's check your different angles if you want. Look how cool it is. And that's what we're doing here.
Were we not writing this down?
What?
Were we not? I thought we were going to actually solve the problem.
Let's solve the problem.
Oh, no. I was writing it down. Sorry, I thought we were going to do it.
No, we're going to write down everything. Don't worry.
Cool, it's not a problem.
So, let's do the same thing we always did. Step 1, sketch the graph. Here is my graph. I will copy it. And I will post it here. And I will post it here. Here it is. This is literally a sketch. They gave us the cardboard. They gave us the size of it. What size was it? What did you say? 10/16, right? 12/2. Did you say 12/2? So, now, we don't know how much to cut. If you don't know something, how do you call it? Like, what does she mean? No, how do you call things that we don't know in math? X. Let's call it x. We don't know how big the cut is, so let's call it x and say that we are looking for x to know how much to cut. The problem itself says find the dimension of the box that maximizes the volume and then find its maximum volume. So the volume depends on the cut. I just showed it to you in the animation, right? So let's call it a cut x. We don't know, like not the whole thing, but like the first slice with the scissors you make. Let's call this x. Because when you fix that x, all other sizes of that squares you're cutting off will be the same. If this is x, this is also x, and this is 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 x. So that's what the problem says. Just cut the same squares everywhere. And since they're squares, it's just convenient to call it x. So let x be a cut size of the side of the cut. I'll just call it cut, but you understand it's the side of each cut in centimeters. That is my new variable I'm creating. Now I need to figure out when I'm folding what happens to all of this. So we have fixed dimensions of the original cardboard. We have 10 and 16, but the box will be different. When you're folding it from the animation, you can see the cuts will go up, so the whole width becomes shorter. This is a nice illustration here. This will be the side of my new box. So if the whole thing is 16, what is the side of only blue part? 16 minus 2x. Do you see that? 16 minus x cut on the left and minus x cut on the right. Let's call this side length. Length is 16 minus 2x. That is length. Again, if we messed up and length will be shorter than width, math will show us later. So let's call this length over here. How about the other side? The other side was 10. If it was 10, and now we're folding it from cutting 2 x's from each side, the new width will be 10 minus 2x, right? Width. Width of the folded box, not of the cardboard. So 2x are 2 cuts from the left and from the right. Those are my sides. Then I'll put this W here. So, and then what are we looking for? What are we maximizing here? The volume. Let's call it V. That's the volume. To maximize the volume, we need to know the relationship between all these 3 variables we just created. We actually have 4 variables, X, L, W, and V. Volume equals what? Actually, before I'm asking this question, we have volume. Volume is a 3D characteristics. Volume have correlationship between length, width, and
Height.
where is my height?
Yes.
How do you see it's X? It's so smart that you got it right away, so I want to kind of make sure everyone did. For me, it was a big surprise when I was learning this, like, oh, that makes sense. You need to have some visual engineering mindset, I think. Or maybe just play with games a lot. Width and length are on the picture. The height of the box will be as high as the large my cut is. So my height, h, is x. The more I cut off, as you can see from this animation, if I have a 0 cut, it will be flat. If I have a big cut, it was flat. The more I cut off, the higher the box goes, the taller the box goes. If I cut just a little bit, then it doesn't go very high. So that is my height. My cut is my height. Pretty cool, right? So what is the volume then? What's the formula for the volume? And H. Thank you. L, let's not call it capital L. That is unusual. Small l. So L, W, and height. And now we can rewrite everything. So, okay, let me write down that this is what we want. This is what we want to maximize. To maximize. This is my objective function. Objective function, by the definition, is the function we need to optimize. In this case, maximize. I will like to differentiate it and so on, but it has 3 variables now. That is definitely too much. So I will rewrite it in terms of x, bless you. V is, L is 16 minus 2x, that's my length. Total 16 minus 2 cuts. W is 10 centimeters minus 2 cuts. And then height, we all agree, was x. Now, it's actually a cubic function. It's fine if you don't see it, but it's x times x times x makes a cubic function. This is the function we want to maximize. Put it in the box. We'll see. So this is the one we want to maximize. Very nice. Then, are there any other constraints? Not really. The only constraints we use are 10 and 16. So there are not more things to cut than 10 and 16, which means x actually has a domain. From here, I can immediately write down in red that x has the domain. I definitely can only start from positive, so including or excluding zeros, but 0 cut will have no volume. 0 height will give me volume 0, because it will be multiplied by 0. And then what is the biggest cut I can make? Interesting if you can guess.
5.
How did you get 5? And why not 8, for example? Or 10?
Half of 10.
Half of 10.
If you cut all the way to no.
It will be too much, yeah?
8.
So that's the thing. You do know that this should be positive, right? This should be positive, and this should be positive. Choose the smallest one and make that positive, because the smallest one should be positive. The smallest one is 10 minus 2x, right? If x is 5, 2 times 5 is 10, 10 minus 10 is 0. So at least x should not exceed 5. If it is 5, width will be 0. You will cut exactly half of the width. Think about it. From both sides, it will be half of the width. There's no width. If you cut 8 over here, it also will make it 0, but you cannot cut 8 here because 10 minus 16 is negative. So domain showed up. Domain is the natural restriction for this applicational problem, which is how much I can cut. So you simplify, just like Chris mentioned, maybe we should distribute everything, and I'll help you out with this. 4x cubed minus 52x squared plus 160x. That's just lots of algebra, so you distribute everything. Finally, the calculus part starts. We want to take the derivative, set it equal to 0, and solve it. 4 times 3, 12x squared minus 104x plus 160. Put it in the box. This is your derivative of the volume function that depends only on the cut. How interesting is that? No? No, yes. Set it equal to 0. This is the quadratic equation. So there's no D and E, by the way. Quadratic equation. You can use the quadratic formula. If you remember, there's a song for the quadratic formula. Or you can use any other ways to solve it. So I would divide by 3, by the way. Don't you think so? If you have division by 4, divide by 4, it will be 3x squared minus, just a second, 26x plus 40. And then you use quadratic formula. Yes. Any questions?
20 over 3.
Oh, you're so fast. Just a second, let's wait for everyone. But yeah, we're almost there actually. Exactly 2 minutes enough to finish. Quadratic formula x equals minus b, so 26 plus minus a square root minus 26, don't forget parentheses, minus 4ac all over 2a. So it's 6. Anyway, calculations of the algebra class. And you will have 2 solutions, 26 plus or minus 14 over 6. And you hope that one of the solutions is negative, because then it will be not in the domain. x1 is 20 over 3. Okay, that's positive, so maybe. And x2 is 2.
Well, we can't exclude. We can exclude one of these.
So, yeah, that's weird. Why we have 2 solutions? Because cubic functions have several actually two critical values. We need to check the domain. 20 over 3, is it smaller? It's bigger than 0, but is it smaller than 5? No, because 6 times 3 is already 18. This is greater than 5, not in the domain. Not in the domain. So, kicking this out, drawing the sign line. What kind of expectations do you have about the sign line? V prime. Putting 2 on a sign line, we're going from 0 to 5. So, check the test points. What expectations do you have if we're maximizing?
Up, down.
Up and down. And I will just skip the whole process because you're doing homework on this anyways. This is maximum. Since it's the only critical value on the domain, we have first derivative test, or you can do second derivative test, by the way, to check it as well. Second derivative, v at 2 is negative, or we can do a closed interval method if you want, since we know the ends. But to be honest, we know the solution now, so we can answer. A famous open box problem. It's, to be honest, taught everywhere in the United States. All schools in the United States teaching this problem. So interesting. Lengths. So we found x, right? X was height. Height is found as 2. Length was 16 minus 2x. That is 12. Width was 10 minus 2x. That is 6. This time we guessed correctly. Length is longer than width, so we did good job. All in centimeters, centimeters, centimeters. And then volume is height times length times width in any order you like. Multiply them out. 12 times 6 times 2, what did you say?
144.
Thank you, good job. 144, what is the unit? Cube, centimeters cube. So the box looks like so. Well, actually just a box. What do you expect from it? It's a box with no lid, with height 2, length 12, and width 6, and the volume 144. Good job, people. This is the box that optimizes, maximizes the volume, by the way. What?